So, good evening, everyone, and welcome to the Royal Society and to the 2018 Milner Lecture. I'm David May, and I'm the chairman of the Milner Award Committee. And I'm here to introduce Marta Kwiatkowska, who will receive the 2018 Milner Award. This award is given annually for outstanding achievement in computer science by a European researcher or a researcher who has had European residency for 12 months. And in case you're wondering about Brexit, European is defined by membership of the Council of Europe, which predates the European Union and has far more states. The recipient of this award is chosen by the Council of the Royal Society on the recommendation of the Milner Committee. The committee has members from the Royal Society, the French Académie des Sciences, and the German Leopoldina. It's supported by Microsoft and named in honour of Robin Milner, who was a pioneer of computer science and a Turing Award winner. And I couldn't help noticing today that Robin and his students made major contributions to the theories, tools and techniques that are being used to ensure the correct operation of computer hardware and software, especially systems with many interconnected components. And this year's lecture, in fact, addresses a very similar topic. I'd like at this stage to give Chris Bishop from Microsoft the opportunity to say a few words, because he'd like to. So over to you, Chris.
Thank you, David. Good evening. So Microsoft Research is delighted to support this award in memory of Robin Milner. Robin was a Fellow of the Royal Society. He was a recipient of the Royal Society of Edinburgh's Royal Medal for bringing about public benefits on a global scale. Robin was also my neighbour in Cambridge when he moved there, and someone I knew personally. Of his many achievements, perhaps most notable was his Turing Award in 1991. This was awarded for 3 distinct achievements. LCF, the mechanisation of Scott's logic of computable functions, probably the first theoretically based yet practical tool for machine-assisted proof construction. ML, the first language to include polymorphic type inference together with a type-safe exception handling mechanism. And CCS, a general theory of concurrency. In addition, he formulated and strongly advanced full abstraction, the study of the relationship between operational and denotational semantics. Since 2012, led by the Royal Society, the Milner Award has been recognising outstanding achievements in computer science by a European researcher. This has brought to the fore some incredibly interesting and inspiring work, ranging from research in programming semantics, machine learning, and formal verification. Today, we continue the tradition of highlighting and rewarding exceptional research. And so I'm delighted on behalf of Microsoft Research to offer my very warm congratulations to Marta on the Milner Award. Thank you. Thank you.
So I'd now like to introduce Marta Kwiatkowska. Marta is a professor of computing systems and a fellow of Trinity College, Oxford. She has made fundamental contributions to the theory and practice of model checking for probabilistic systems, which have to operate in an unpredictable environment. They may even be surrounded by people. She led the development of the PRISM model checker, the leading software tool in the area. Probabilistic model checking has been adopted in many fields, including distributed computing, wireless networks, security, robotics, healthcare, systems biology, DNA computing, and nanotechnology, with design faults found and corrected. Marta is a fellow of the Association for Computing Machinery and a member of the Academia Europaea. So after the lecture, I will present Marta with her medal and scroll, but now we're going to hand over to Marta. So ladies and gentlemen, I'm very pleased to present Marta Kwiatkowska to give her lecture.
Good evening, ladies and gentlemen, distinguished guests. Thanks to the chairs for the very kind introduction. And I would like to start by saying that it is a great privilege to be giving this lecture, and I would like to offer this lecture as a tribute to Robin Milner. Robin Milner had the great foresight to see the importance and potential of computing as a discipline, and especially theory within it. And I'm going to touch upon both in my lecture. But first of all, these are really exciting times for computer science, really, really exciting times for our discipline. Robots roam everywhere. They are taking over the tedious tasks, they are taking over the dangerous tasks, for example, motorcycle testing. Drones are delivering parcels, they are working on farms, and in Japan, care robots are being introduced. The vision of the robotic assistant is getting nearer. It's probably not quite there yet, but it is getting nearer, and robots are becoming proper members of our society. Now, as computer scientists, we are also very aware of the limits of the computing medium, conventional computing medium, the silicon. And because of Moore's law, we are beginning to look elsewhere. And in particular, we are looking towards chemistry and developing DNA computing. Now, DNA computing works on a very different paradigm. So rather than looking at encoding of bits in terms of high and low voltage, what we need to do is we need to think of computing as computing in a test tube, computing with soup. You have a soup of molecules. Some of these are distinguished as inputs, others as outputs. And if you choose them well, then the process of transformation, which proceeds through chemical reactions, will produce your output. Now, where are we in terms of the state of the art? What the scientists at Caltech have shown is a computing device made from about 130 strands, which can compute the square root of a 4-bit number. Okay. But they have made this year much more progress with neural networks. They have developed AI in DNA, which can already recognize handwritten digits, the MNIST example for those of you who know about it. Now, if we move further, the nature of our discipline is changing. It used to be the case that hardware defined everything, and it set the limits. But now the boundaries between hardware and software are changing, and we are now using software techniques, software methodologies in order to design hardware. For example, even the ARM microprocessor. But again, the biggest change of all is that we have deep learning with everything. Face recognition, Google Translate, Alexa, you name it. Deep learning and AI seems to be taking over the world. But the biggest excitement is, of course, self-driving cars. It is not just the biggest excitement, it is also the subject of a great debate. What I'm showing you here is a dramatized vision of what a rush hour in future might look like. Okay? Now, these perfectly synchronized humans and cars, perfectly aware of each other, just communicating by wireless signals. Okay, right. But if you've ever tried to cross a road in India, okay, it doesn't look that much different. Okay, but of course, the current state of the art in autonomous driving looks a little bit different than what I showed you. Here is a video which is from an autonomous car that was designed by my collaborators at the Oxford Robotics Institute, and it's driving around Broad Street. Many of you would be familiar with it, just outside Trinity College, which is my college. What you can see here is a piece of control software which works by environment learning. I'm showing you day 4 because by day 4 it has learned to recognize the environment and it can identify the pedestrians and cyclists much better. Okay. So autonomous driving is of course presenting us with a huge challenge. It is a very complex engineering and AI problem, but software is at the heart, and software is the brain of all the robots and autonomous cars and everything that I've showed you so far. What engineers use in order to design these self-driving cars is a mix of technologies. They use the old, try and test it, for example, control theory, and they mix it with new technologies, in particular computer vision, which involves now deep learning, prediction, path planning, etc. Now, because the problem of driving, if you just think back to the scene, in the rush hour, it's a very complex scenario that the car has to deal with. And it is impossible to actually enumerate all the cases. So instead, what is happening is we are introducing deep learning techniques because machine learning is very good. It really excels at discerning very, very small differences in patterns. So what is happening is that NVIDIA, for example, is producing a GPU device which is automotive grade, and it actually sits in the car and runs the software. But instead of developing the complex software by programmers, what we do is we have to have access to very high quality data. That data either comes from human-driven cars or it is perhaps painstakingly labeled by humans. So we have shifted the complexity of programming from combinatorics to really finding high quality data and training it. Okay, that's self-driving, but I wanted to ask you a question. Would you trust a self-driving car? So can you raise your hand? Okay, very good. Who wouldn't? No, it's very good. It's fairly even. Okay. What I'm showing you here is a Waymo Early Riders program. If you live in Phoenix, Arizona, you can join in. If you live in California, you can also test Tesla and Uber. And of course, near you, you will be able to see 5AI. In Oxford, there is Oxbotica, and Oxbotica is already running, between London and Oxford. So great, this is all very good, but you have probably heard about these. So earlier this year, there were 2 fatal crashes. One was a crash by Tesla with the autopilot mode. It just crashed into a barrier on a motorway. And we don't know exactly what happened, but perhaps it didn't see the white lines that it was trained on. The other crash was a fatal crash for a pedestrian while there was an Uber being tested, and the Uber had a test driver in the car. But what happened was that even though the software spotted the pedestrian 6 seconds before, the emergency brake was switched off. Apparently, this is part of the procedure by Uber to avoid erratic behavior. Okay. So perhaps we just stop there. It is not my intention to scare you. I wanted to mention these because, of course, the problem itself is a very, very complex AI safety problem. And what is different compared to conventional software development is the fact that we have many agents. Just think about the rush hour. Many agents, they each have their own goals. These goals conflict, but they are autonomous. They are autonomous. They make decisions by themselves, for themselves, and we have to take all that into account, together with all the additional aspects such as situation awareness, etc., etc. But the situation is safety critical, as these crashes demonstrate. It is really safety critical, so what we need is guarantees, okay? Guarantees. And what we also need is if failure occurs, there has to be accountability. Okay, and this brings me to what I have been working on for the past nearly 20 years now. I've been working on developing formal, provable guarantees for the correctness of software, starting from very simple questions such as, does the program terminate, to much more complex properties that are expressible using temporal logic. But what we do, we actually have to resort to mathematics. We have to resort to rigor and mathematics, where when we take a program, we have to develop an abstraction, a model, an abstract model of that program, and that model can take different forms. It could be a very simple automaton, a transition system which jumps between the states, or it can even be a formula, for example, a differential equation, or a neural network. In fact, in most systems, in most self-driving cars, you will have a mix of all three. You'll have a mix of all three. And once we have a model, then what we do is we want to verify that that model satisfies a given specification. So essentially, we want to do mathematical proofs. But we want to do these proofs automatically. Automatically, that is by means of an algorithm which runs on a computer. And what we also want to do, in addition to verification, we want to be able to synthesize, to generate a program that's guaranteed to be correct by construction. That's called synthesis. And for myself, I have focused on probabilistic guarantees, because the world out there, including the world of autonomous cars, is stochastic. You have a lot of uncertainty in the environment, in the behaviors. There is risk that has to be considered and quantified. But in addition, software also uses randomization. Believe it or not, a lot of programs and protocols actively use random choices. You can think about it as using, coin tossing in order to take the next step. And once you have a model which is probabilistic, what we need is probabilistic guarantees and quantitative guarantees, because we need to be able to compute the actual probability values. And there is a whole range of properties that can be expressed. I've already mentioned risk, but also safety, security, reliability, performance, resource usage, trust, authentication, you name it. They are all expressible using probabilistic logics. Now, my focus has been on not just developing probabilistic models, that's just the first step, but really on developing automated tool-supported methodologies with which you can devise these models, analyze them, that is, verify them, and synthesize them. And this has resulted in the probabilistic model checker PRISM, which was developed, and it won an HVC award jointly with Dave Parker and Kathy Norman, and they are both here. Now, this has been applied to a wide range of systems because probability is pervasive and it underpins many sciences, not just computer science. But rather than tell you what PRISM can do, how PRISM does it under the hood, which you can find out by looking up lots of publications on this website, what I want to do instead is I want to take a Monty Python turn, okay? Who have asked, what have the Romans ever done for us? I want to say, well, what has probabilistic verification ever done for us, okay? So that will take me away from self-driving to start with, but I promise I'll come back to self-driving to finish off. Okay, so I have selected a very small set of examples, and I will tell you at a high level in what way these models and verification and synthesis tools are helpful. And I will start with an example which is sitting in most phones and other mobile devices, and it is a very tiny component. It is very tiny part of the Bluetooth protocol, which we analyzed in 2006. But it is still probably the most complex protocol that we have analyzed. What this protocol does, it does a very sophisticated switching between frequencies, but because there are two devices that have to talk to each other on the same frequency, there has to be a scheme of avoiding the frequencies and then also checking for collisions. So to make sure that the devices don't keep coming back at exactly the same time, they use random weight. They use random weight in order to decentralize. And what we did is we managed to build an exact model, an exact computation, but it is absolutely huge. It's 32 very huge Markov chains with 11 billion initial states. So sampling is just impossible to apply in this case because you just can't get this information. But with this, we were able to prove the guarantee, and the guarantee is surprising. So the worst case expected discovery time is 5 seconds, okay? And you can actually pinpoint precisely the starting situation which would lead to that time. Okay. My next example is a real safety-critical example. And the reason I'm showing you this is also because of the trend that I've mentioned, that hardware is slowly becoming software. And in fact, a cardiac pacemaker, which is an implantable device which is implanted under the skin, and its job is to monitor the heartbeat of a patient and insert artificial beats when there isn't one detected for a certain amount of time. This device is now increasingly becoming programmed by software. And in fact, there is this report, I didn't make up the title, Killed by Code is the title of a report, which has pointed out the fact that FDA, the Food and Drug Administration in the US, which licenses medicines and medical devices, had to recall 23 defective pacemakers, and 6 likely caused death, and they were recalled because of software defects. Okay? This is just because of software defects. So what a pacemaker actually has to do, it has to be able to count time and monitor the electrical flow in the heart. So what does verification actually have to involve? Well, if you have a pacemaker, it is an open system. In order to actually verify the behavior of the pacemaker, you have to close the loop. You have to provide the model of the heart. So the idea is that, okay, we model the pacemaker, but then we also need to have a model of the heart, but we want to have a model of the heart which we can adapt to the behavior of a patient. And in fact, we have a whole range of models of the heart. The pacemaker itself is a timed automaton. Later it also becomes a timed hybrid automaton for anyone who is interested in that. And we have the model of the heart, and then they are composed. We have a well-defined synchronization between these two. And then what we can do is, for verification, we can actually show the basic safety. And the basic safety for a pacemaker, a sort of standardized default safety, is that there are between 60 and 100 beats per minute. But you can also provide an analysis of energy usage. And why is this important? This is because these devices are implanted for something like 6 to 7 years. And if you use less energy, if you can use less energy, and in fact we are all different, we have slightly different ECG patterns, so if you can use less energy, that person is not going to need the replacement so often. What we can also do is we can provide advanced guarantees. So there are rate adaptive pacemakers for patients whose heart doesn't adapt. And for those, we can show advanced safety. But in addition, what we can do is we can replace the testing of these pacemakers, which is done with real people and real patients, with in silico testing, with testing using the models. So just to give you an idea what this might involve, okay, this is now my model. This is a simplified model of the heart and the simpler pacemaker that I'm showing you. And it's showing a synthetic ECG. So this is a copy of somebody else's ECG, and you can now use it for pacemaker testing. So if I take a heart which has bradycardia, this is a slow heart rate. As you can see, this is potentially fatal because there are some beats that are missed out. If I now compose it with my pacemaker, you can now see in red the beats that the pacemaker has added. Okay, so this is the result of a verification. But one issue with verification is that if it verifies, that's great. But if the answer is no, this property is not satisfied, what do we do? Okay, we would need some additional information. This is called counterexamples, and then we may need to go back and fix the designs. So instead, we are turning the question around, and we are asking, can we synthesize the model and the pacemaker that would guarantee that the property is satisfied? This is a very difficult problem, and it's very difficult to state that problem. So what we are looking at is we are looking at a simple variant of the problem where you have a template design which has gaps for some variable values. And in my case, this template just has gaps for a delay. How long does the pacemaker wait before issuing an artificial beat? Now, as I said, we are all different. We have very different ECG. For some people, this is the pacemaker can wait longer. For others, it would need to pace more frequently. So the question now becomes an optimization question. Can I adapt the pacing rate by learning from the patient's ECG, but then compute the delay, the actual delay, so that the energy usage is minimized? But it is also possible to maximize a measure of cardiac output, which is a measure of efficiency. Okay. And this is something that we were able to do. And in fact, we were able to improve over the default values. And to show you what this might lead to, imagine, okay, the energy, as the delay is longer, the less energy you use, okay? So that's the blue plot, and the cardiac output is the other plot. But of course, they are conflicting, so you might need to consider the best trade-off. And as you can see, the first trade-off is so-called overpacing. Okay, the pacemaker does a lot of work, but it uses a lot of energy. In the middle, you have, a very good optimal trade-off. And at the end, because we say we are going to use very little energy, that person may actually die. Okay, right. So from the pacemaker, I wanted to show you some other types of usage. And this is perhaps a little bit of an unusual direction because I'm now veering into the world of security and, in fact, authentication, biometric authentication. There is a company in Canada called NIMI, and that company actually introduced ECG biometrics. The band that I'm showing you is something that people can wear, and when they start, the ECG will be taken and the template will be initialized, and then when the person wants access, to the room or perhaps access to the payment, then the ECG is checked against that template. And I was just talking to Ivan Martinovic, our security expert, and he said, well, let's try to break it. So this is what we did. It's the same model, okay? Before I was showing you what the model can do for verification. It's the same model. Now it can help with an attack. How? Well, if I can produce a synthetic ECG, I can use that synthetic ECG in order to impersonate a user. That's a very simple thought, and in fact that worked. What was not that simple is that you actually then have to generate the wave, okay? So you actually, because to break into the actual device, you have to generate the wave. So what Ivan Martinovic's group did is they used the music synthesizer. and an audio input in the end in order to break the protocol. This was all done under responsible disclosure, but it's a result. There are various kind of countermeasures. For example, don't rely on ECG on its own. You need multi-factor authentication. And okay, the story didn't finish. So if you ever thought that you are safe with your fitness tracker, then perhaps you can think again, because this attack, which was produced by ECGs, can actually transfer in a sense that I can collect data. We are all walking data factories. You know, the mobile smartphones, they are fitness trackers, they are recording a lot of data about us, and that data is also available, sometimes available, you know, for a population. What it is possible to show is that if you have data collected from different sources, you can still attack the original source, okay? So beware of your fitness tracker. Okay, my last example, before I go back to self-driving, is DNA computation. Okay, what I'm showing you here, in the middle you see a tile. Okay, it is a tile. What you see on the left is how that tile is formed. It's formed by a single circular DNA, which is then paired up with so-called staples, short sections of DNA, and they are designed in such a way that they bind precisely in this position, and you end up with a tile. And you can see the picture, NFM picture of the actual tile on the right. Now, this is described as a molecular breadboard. Okay, have you heard about the silicon breadboard? You know, where you lay out your circuits. Okay, we can use this tile to then lay out a circuit. A circuit would be DNA molecules laid out in a decision tree pattern. And what my collaborators, Andrew Turberfield, in his lab, he also knows how to make these molecules walk. So you attach the molecule at the start of your circuit, and you control the movements of the molecules, for example, by enzymes, and you just wait until it gets to the end. And this is a diagrammatic picture. I start where there is the Q end, and you detect with fluorophore where you get to the end. But these molecular walkers, because they are tiny, they are highly unreliable. Highly unreliable, in fact, they fall off tracks. So what we did is we then employed the parameter synthesis to actually synthesize, compute the rates for the walkers, which guarantee a given level of reliability. But the tile itself was also the subject of a study, and the question that we studied there, and this was a joint collaboration between Andrew Turberfield's group, the experimentalists, and us modelers. And the question was to try to identify what it makes, for the DNA to fold into a particular shape. And what we did here is we actually took 2 copies of this circular strand, identical copies. So the staples had exactly 2 positions to end up. And then we did experiments to find out what happens. And these tiles ended up in different configurations. I'm showing you some examples here. And interesting thing was that with a model, which is a very abstract model, so the model doesn't take into account any spatial information or spatial dynamics. All the model does is represents each staple either in position, in a binary form, either in position or floating. And this is an absolutely huge number of states, and it is a probabilistic model because we have to take into account the kinetics, but also we have to take into account thermodynamics. And with this, we were able to experiment with the tiles by actually cutting parts of the tiles to check whether it will misform in a particular way. The model turned out to be predictive, and it is reproducing the shapes in a fairly good way. Okay, so this was just a quick tour of a selection of examples, and I just want to finish off with autonomous driving, which I imagine is the topic that brought you all here. Okay, so what I'm showing you is what an autonomous car actually sees. Okay, it sometimes uses a camera, but it can also use a LiDAR or radar, and that's an image of a LiDAR. These boxes are bounding boxes. They, come from vision. And of course, if you think about failures, like the ones that I've shown you, there could be many reasons for those failures. There could be a sensor failure. There could be a failure in this object detection software. But as I've already mentioned, autonomous cars rely on machine learning, deep learning, to perform vision. But what is not known to people outside machine learning is that machine learning software doesn't come with any guarantees. It's just not part of the science of machine learning. Okay, and for me, as a scientist, when I started working with Oxford Robotics Institute on this, I realized that there was an opportunity, and perhaps I would like to invite you all, because there are plenty of opportunities for people in verification to study this. But why should we worry about safety of self-driving and, to mention the Tesla and white lines? Well, this is because deep neural networks are very susceptible to what is known as an adversarial perturbation. These are very tiny, tiny changes, imperceptible to humans most of the time, very tiny changes, but they can change the classification of the network to something catastrophically wrong. And the example that I'm giving you here is actually an example of taking an image. This is an urban scene, and working with a winning network of the challenge. This was the winning network of the challenge. You can change 1 pixel in that image to green, and it changes the classification from red to green. I don't need to explain what this might lead to, okay? Now, what you can also do is you can reduce the official accuracy of such a network to 0%, okay? Now, when these networks are introduced, there is a way to estimate the accuracy. But this is computed for a finite set of test data, finite set, and that set, this is under the assumption that the distribution in that set follows the input distribution. And that's a hidden assumption that everybody knows about. But hidden distribution is unknown most of the time. So that assumption is very difficult to guarantee. So what I'm saying here is if I take a finite set, if I can manipulate each point in the set in an imperceptible way to change the classification of the network, I'm reducing the accuracy to 0%. Okay? That's not hard to do. Actually, it's hard to do it fast. Each of these takes about 3 seconds to find the 1 pixel, but we have to combine it with computer vision techniques. Another example is traffic signs. You can see here images of traffic signs and slightly modified ones. Okay, I admit the modifications are artificial because they are done artificially, digitally, using our software, but just think of wear and tear, think of rain, think of snow, okay? And you can see what this might do. And what I'm also showing you that sometimes these come with confidence which is as high or even higher than the original confidence. Okay. So what do we do? Well, so what I have been working on is trying to come up with guarantees for deep learning. And this is the archetypal MNIST handwritten digit data set. But the idea is that I want guarantees, so I'm just starting with simple proofs. And my simple proof is if I take an input and a neighborhood around the input, what I want to be able to prove that however I change the pixels around, in that region, this will not change the classification of the network to anything. Okay, so it's a kind of invariance within the input. But we can go further. What we can also try and do is we can compute the maximum safe radius around the point, okay, such that within that radius there are I guarantee there are no adversarial examples, okay? And we do it by computing lower and upper bounds, and I'm showing you here the convergence, okay? But what we actually need for machine learning is probabilistic guarantees, okay? The requirement that no adversarial examples exist in a region is too strict. And this is because we have to take into account the data and the training. So what we do need is probabilistic guarantees which quantify the probability that there exists a point in a neighborhood that differs by no more than a threshold. Okay, so that's where I've got to with guarantees. And you might ask, well, have we solved the problem? Is verification, probabilistic verification, going to solve the problem? And I'm showing you some recent news. So Alphabet, that's the parent company of Waymo. Waymo is the Google offshoot. Apparently, locals are frustrated with Waymo cars because they take too long at junctions. They are just too conservative. And another example is, well, should we actually allow self-driving cars to break the law in certain cases to avoid accidents? In fact, the Law Commission, I think, started an investigation last week to discuss this precisely. So what we need is we actually need to be able to make cars behave more like humans. And this brings me to a much wider problem, and that problem really touches upon, I think, the whole infrastructure for self-driving, but also how the self-driving cars will fit in within the society. I mean, when you are driving, you make eye contact, you perhaps wave. Are we going to do that with autonomous cars? Or do we need perhaps a special digital infrastructure for them? We know that trust is something that we naturally develop in relation to humans, but also in robots. But that could lead to overtrust. again, there was an example of a Tesla crash. There are also moral decisions. There is conflict, and accountability needs to be decided. Who is to blame? Is it the manufacturer, or is it perhaps the person who wrote the software? Or do we need a black box? Do we need a black box for autonomous cars in the same way as we have black boxes for aircraft? Okay. So these are all very important questions, and I mentioned them as part of the debate, but I'll finish off with some more questions. Okay. Morality and ethics. So imagine you are programming this car, and you have to make a decision. How do I program it? Okay, should the car go straight ahead and kill lots of people? Okay, or should it just veer to the right, just kill one person? I mean, you might think, well, of course, it's obvious, utilitarian solution. Yeah, okay. But what do you do in this situation? So imagine that you are sitting in this car, or perhaps your child is sitting in this car, and the choice is you either kill the pedestrian or you drive into the barrier. Okay, difficult choice. And here, okay, it's another choice where your utilitarian solution is immediately defeated if you have to choose between your child living or several people living. What I'm showing you is a dilemma that was discovered, and there is a web page and a system where you can actually answer these questions yourself. It's called the Moral Machine, and they have done a study to identify this dilemma, but what they have also done is they have done a global study, and they have discovered that we are all conditioned by our society. So some people are more willing to sacrifice elderly people than others. Just think about the Far East. But what this dilemma is exhibiting, that if you are a programmer, you will go for the utilitarian solution. But if you are buying the car, you want to be safe. You want your child to be safe. So we would have to make a choice, you see, in terms of the guarantees, because we might end up with cars that nobody will buy. Right. Okay, right. So I hope that I have shown you through examples what role probabilistic modeling and verification and synthesis can play, and in a wide-ranging set of scenarios. And I mean, just like you, I'm very excited about the potential of AI, but we need to know the limits, and that applies to deep learning as well. We need rigorous foundations. We need verification, we need safety assurance, and we have a responsibility as scientists to actually start addressing these, start questioning certain situations and addressing these. And of course, for social implications, for this is not something that we computer scientists can resolve for ourselves, but we do need to collaborate with others. So I've greatly enjoyed, my time of working on self-driving cars, but I can promise you there are many, many challenges that remain. And I just wanted to finish with a tribute to Robin Milner. So back in 2007, 2008, I worked with Robin Milner on the Grand Challenge, the Ubiquitous Computing Grand Challenge, and in particular in this very room in 2008, we had a Royal Society discussion meeting called From Computers to Ubiquitous Computing. Ubiquitous computing is where computers, as you know them, disappeared. And I have to say that I think the developments in the technology have surpassed my expectations. I didn't realize we are going to move so fast. Now, Robin Milner said, "Ubicomp can empower us," and I think that was a very foresightful statement. But what he also said is, we computer scientists must keep a live connection between theory and application in computer science. And this is part of a citation of a Milner lecture that I gave a few years ago at the University of Edinburgh. And I wanted to offer this lecture, and kind of my work was addressing these problems, but targeting practical algorithmic techniques and industrial tools. Okay. Thank you.
Very well. So we have a little time for questions, one or two of them. There are some roving microphones, so if you do want to ask a question, please wait until you have a microphone. Carry on over here.
Thank you very much for an extremely interesting lecture, out of which I hope I learned something myself. You have all served to increase my very deep skepticism already about whether we are ever really going to have self-drive cars in the way that's being hyped in the press and sort of semi-advertised by some of the manufacturers. I think the most intelligent question I can ask is that it is said that we will have self-drive cars on the road by 2021. Some manufacturers are saying this. What do you think we'll actually have by then?
I mean, yes, I think you're touching on a very important topic. I think, again, have different types of self-driving. As you know, there is level 3, which is semi-autonomous, that's Tesla. There is level 4, there is level 5. Level 4, I think we will have. Level 3, I think, is proving to be the most difficult, when the driver actually has to be alert and has to take over. Level 5 I really don't know. I think we haven't worked out how to manage the whole situation when I was talking about infrastructure versus what kind of communication. I think level 4, convoy driving, these things will happen. I'm actually positive about this technology. It will happen. I think we just need to make adjustments. I don't think we have fully understood the implications and what is needed in order to push this forward.
Over there.
Hi, Marta. Thanks for an excellent talk. It was really interesting, really far-reaching. Lots of areas you touched on there.
Thank you.
For me personally, the things I found really interesting was this optimization of performance versus energy, and the security work that you've been looking at lately. One thing I did notice, you talked on trust, ethics, and morals, and there's a lot of work in that area, but you didn't mention something that's a little bit interesting at the minute, given legislation, is around privacy. And I wondered, to that extent, have you done anything in your work or know of other works where they're trying to look at that trade-off between performance and data minimization? So how effective your algorithms can be without collecting all of the data that we currently use, especially in an autonomous vehicle sense where there's my own data, passenger data, there's environmental data. And I wonder if some of the techniques you're using could be used to analyze that trade-off between the performance that we need from an algorithm versus the data that we're collecting and using.
Mm-hmm. Well, thank you. Very good point. So no, I haven't worked on privacy, but the answer is yes. And I think if there are any PhD students or potential PhD supervisors listening, then that's an excellent topic to pursue.
Another one? Thank you. Oh, you got the mic.
Thank you. So, very interesting talk. I'm particularly that the probabilistic guarantees sound very interesting. I'm wondering, in terms of regulation, because obviously this kind of technology is going to be subject to regulation. That still seems to be quite early. In Britain, we have a very good tradition of doing very well at particularly safety and safety culture and safety regulation. Do you see regulators or accident investigators or those kind of disciplines getting involved in this? Have you spoken to any of them? Are they interested, or are we still too early for that?
I think that it is critical that we bring in these experts from safety engineering. I mean, in order to engineer a self-driving car, you have to address safety at multiple levels. You have to have safety in the architecture, you have to have fail-safes. For example, like the car would need to stop, but you also need guarantees. You can't have instabilities. If there is potential for instabilities in the behavior of your software, you have to have either monitoring, runtime monitoring, or you have to have something else like, fail-safe. And also, I think we need to learn from aircraft engineering, which is very strongly managed. And of course, the reason that we have black boxes and this very strict process is because of accidents. So I think in order to avoid having more accidents, in the self-driving context, I think we do need to bring in the traditional safety engineering, safety testing processes as well. I mean, if you think of how Uber is testing by switching off emergency braking and expecting the test driver to respond, within half a second, is that acceptable? This has nothing to do with verification. I think this is just weak processes, weak safety engineering processes that are being applied, probably because of overexcitement. People are just so excited to see these things working. They are forgetting about the basics. We need to get back to basics.
Okay, so I think we have probably just one more question at the back. So,
Thank you for your insightful talk on the topic. Actually, my question is a bit more technical. Sorry, can you hear me?
Could you speak up a bit?
Okay. Actually, my question is a bit more technical. Regarding the adversarial perturbations that you mentioned in the earlier slide, because these perturbations are actually very carefully crafted ones and may not actually occur in the real world. Whereas a recent paper actually published that some of the more common things might be a blocked out or damaged road sign with perhaps not so much of perturbations within a certain fixed radius, but rather perhaps a rotation or break or something. So in the aspect of verification, has there been any work done yet on such adversarial examples, as opposed to the one that you showed in the slide just now?
Okay, so can I repeat your question, because I didn't hear it very well.
Yeah, sure, sorry.
But I expect you are saying that the adversarial examples that I showed were artificial.
Yes.
Yes, okay. Absolutely correct. Yes, they are artificial. They are digitally constructed. They are to make the point, basically, of where the weaknesses are. But what we do need to focus on, and yes, there is a paper from Ian Goodfellow about physical attacks. There are some attacks that I might be showing you which will not matter. What matters is physical attacks. No, I haven't seen any work from verification, but that's obviously a very important direction. There will be a subset of attacks that we really need to worry about, and I think we should be developing techniques targeted at those. But in my early work, I'm dramatizing.
Okay, I think we better stop there, actually. So let me thank you very much for a very interesting and topical lecture. I think you've very much demonstrated the ability to keep the live connection between the theory and application, and you've brought your work to life for us. So thank you very much.
Okay.
And now there's one more thing that's very important that I have to do, which is to actually give Marta the components of the Milner Award. First, obviously, congratulations on this award. It's a great achievement to be given the Milner Award. And I think we have 2 items down here. There we go. So I think you get a medal, and you get a scroll. There we are.